A major bank tests a new AI credit model on 40 customers, and the results look highly promising. The default rate drops from 8% to 6%. The manager reviewing the files is thrilled and immediately prepares to deploy the algorithm globally. But there is a massive leap of faith happening in that office. The bank wants the truth about an entire population, but they only have data from a sample of just 40 people. That 2% drop is a fact, but small groups naturally fluctuate. Did the AI identify safer borrowers, or did they just get lucky? Businesses cannot risk millions of dollars on a lucky streak. They need a rigid, mathematical way to separate the true signal from the background noise. To find that truth, statisticians put the data on trial. They use a strict framework called hypothesis testing. Every trial starts with a defendant. In statistics, this is the null hypothesis. It is the absolute, unflinching assumption that nothing interesting is happening, that there is zero effect, zero difference. Innocent until proven guilty. These overlapping curves represent our starting assumption for the bank. The math explicitly assumes that the new AI model performs exactly the same as the old model. Against this, we have the prosecution, the alternative hypothesis. This is the active claim that the new model actually is better and that a real, measurable improvement exists. The 40 customers from the pilot program serve as the physical evidence. To weigh that evidence, statisticians calculate a test statistic, a single number that measures exactly how heavy the data is against the default assumption. The goal of this trial is not to prove the new model is flawless. The goal is to see if the evidence is heavy enough to crush our default assumption of innocence. This curve maps out all the possible outcomes if the null hypothesis were actually true. The p-value tells us exactly where our evidence landed. Assuming the new AI is useless, what is the probability we would see a drop this large by pure chance? That red line is the significance level, commonly set at 5%. If the p-value falls below that line, we decide the result is simply too bizarre to be a coincidence. We reject the null hypothesis. But juries make mistakes. No matter what verdict the math delivers, there are exactly two tragic ways this decision can be wrong. First is a type 1 error, a false positive. We reject the null hypothesis when it was actually true, the equivalent of convicting an innocent defendant. For the bank, this means launching the AI model globally, only to discover the initial test was a fluke. The model fails, and millions of dollars are wasted chasing a ghost. Then there is the type 2 error, a false negative. We fail to reject the null hypothesis when it was actually false, letting a guilty person walk free. In this scenario, the bank shelves the AI model entirely. They throw away a genuinely revolutionary tool simply because the pilot test failed to detect its value. Hypothesis testing does not grant absolute truth. It forces us to mathematically define our threshold for pain and choose which type of catastrophe we are more willing to tolerate. Watch this seesaw. If you tighten your rules to prevent false positives, you automatically make it harder to detect a real effect, increasing your false negatives. Alpha and beta move in opposite directions. We want a detector with high statistical power. That is the system's true sensitivity, correctly flagging a real difference without raising false alarms. To beat the trade-off, we slide sample size up. The curves narrow and separate, lowering both errors simultaneously. Testing 40 customers simply lacked the power to prove a 2% drop. A larger sample shrinks the mathematical margin of error, making the true signals stand out clearly against the background noise. Raw data without volume is a blur. Scaling the sample size is what sharpens the lens. This leads to the most common trap in all of statistics. Failing to reject the default assumption does not mean the default assumption is true. A not guilty verdict does not prove innocence. It only proves the prosecution lacked the evidence to convict. If a test fails to find an effect, it's often because the test was simply too weak to see it. This exact framework governs how we understand the modern world. It dictates whether the FDA approves a new, life-saving medicine or whether a tech giant rolls out a new algorithm to 1 billion phones. We can never achieve perfect certainty, but by rigorously measuring our doubt, statistical inference gives us the solid mathematical foundation to act with confidence in a universe driven by chance.